Tonight, we're going to explore something that sounds almost impossible when you first hear about it. Imagine space itself, the very fabric of reality, rippling like the surface of a pond when a stone drops in. Not the things in space, not the stars or planets or dust, but space itself, stretching and squeezing in waves that travel at the speed of light. These are gravitational waves, and for over a century they existed only in equations, in the dreams of physicists, in the beautiful mathematics that suggested the universe could sing in a way we'd never imagined. The story of gravitational waves is really several stories woven together. It's a tale of human persistence, of building machines so sensitive they can detect changes smaller than the width of a proton. It's about black holes colliding billions of years ago, sending whispers through the cosmos that we've only just learned to hear. It's about Einstein being right in ways even he doubted, and about thousands of scientists working together to prove something that seemed unprovable. But more than that, it's a story about how we've discovered an entirely new way to observe the universe. For all of human history, we've looked at the cosmos with light, first with our eyes, then with telescopes that could see colors we couldn't, wavelengths stretching from radio waves to gamma rays. But light can be blocked, absorbed, scattered. There are things light can't show us, places it can't go, stories it can't tell. Gravitational waves changed that. They gave us a way to feel the universe instead of just seeing it, to detect the tremors of space itself as massive objects dance and collide in the dark. Think about what that means for a moment. When two black holes spiral together and merge, they create a storm in space-time itself. The space around them, through them, becomes a churning sea of distortion, and those waves, those ripples in the fabric of reality, spread outward at the speed of light. They pass through everything, barely interacting with matter at all. They travel for millions or billions of years, growing ever fainter but never quite disappearing, until one day they wash over Earth. And when they do, when these ancient whispers finally reach us, they stretch and squeeze our planet by an amount so small it seems impossible to measure. We're talking about changes smaller than the nucleus of an atom, distortions so subtle that detecting them requires some of the most precise instruments ever built. The fact that we can measure these waves at all is a testament to human ingenuity, to our ability to reach out and touch the untouchable. The journey to detecting gravitational waves took 100 years. It required developing technologies that didn't exist, solving problems that seemed unsolvable, and maintaining faith in an idea that many thought would never be proven. Along the way there were failures and false starts, moments of doubt and decades of patient work. Scientists built detectors that weren't sensitive enough, dealt with noise from everything from earthquakes to passing trucks, and slowly, methodically, improved their instruments year after year. What's particularly beautiful about gravitational waves is that they connect the largest and smallest scales in the universe. The waves themselves are generated by some of the most massive objects we know of. Black holes with masses dozens of times greater than our Sun. Neutron stars so dense that a teaspoon of their material would weigh as much as Mount Everest. These cosmic giants create waves that stretch across the entire universe. Yet detecting them requires measuring distances smaller than anything we can see. Changes so minute that quantum effects become important. In a way, gravitational waves are the universe's way of telling us stories we couldn't hear any other way. When two black holes merge, they don't emit light. They're black holes, after all, places where gravity is so strong that nothing, not even light, can escape. Without gravitational waves, these cosmic collisions would be invisible to us, silent dramas playing out in the dark. But because mass and energy can curve space-time, and because accelerating masses create ripples in that curvature, we can now witness these events, feel their echoes washing over us from across the cosmos. The implications of this are still sinking in. We've opened a new window on the universe, one that shows us things light never could. We can probe the hearts of galaxies where dust and gas would block our view. We can study black holes not by what falls into them, but by how they shake the universe when they merge. We can even look back toward the beginning of time itself, potentially detecting gravitational waves from the first moments after the Big Bang, waves that have been traveling through space for nearly 14 billion years. But perhaps what's most remarkable about gravitational waves is how they remind us that we live in a dynamic universe. Space isn't just an empty stage where cosmic dramas play out. It's an active participant, capable of carrying information, of being stretched and squeezed, of ringing like a bell when struck by massive events. The detection of gravitational waves proved that spacetime isn't just a mathematical construct, a convenient way to describe gravity. It's as real as the ground beneath your feet, and it can ripple, wave, and carry messages from the most violent events in the cosmos. As we continue our journey tonight, we'll explore how Einstein predicted these waves over a century ago, even though he wasn't entirely convinced they were real. We'll follow the long, difficult path from theoretical prediction to experimental confirmation. We'll meet the incredible machines that finally detected these cosmic whispers, and we'll listen to the stories they tell us about black holes, neutron stars, and the nature of space and time themselves. So settle in, let your breathing slow, and prepare to drift through a universe that's far stranger and more wonderful than we ever imagined. A universe where space itself can ripple and ring, where black holes can sing, and where patient humans with impossibly sensitive instruments can hear the music of the cosmos. The story of gravitational waves is ultimately a story about connection, about how events billions of years ago and billions of light years away can touch us here and now, sending tremors through our world that we've only just learned to feel. In 1915, while the world was consumed by the First Global War, a German physicist was quietly revolutionizing our understanding of the universe. Albert Einstein, working mostly alone, was putting the finishing touches on what would become his masterpiece, the general theory of relativity. Hidden within the elegant mathematics of this theory was a prediction so subtle, so strange, that even Einstein himself would spend years doubting whether it was real. That prediction was the existence of gravitational waves. To understand how Einstein arrived at this remarkable idea, we need to first understand what general relativity tells us about the nature of gravity itself. Before Einstein, gravity was understood through Isaac Newton's laws, which worked beautifully for almost everything. Newton described gravity as a force, an invisible pull between objects with mass. The sun pulls on Earth, Earth pulls on the moon, and everything with mass pulls on everything else. It was simple, elegant, and incredibly successful at explaining the motions of planets and the fall of apples alike. But there were problems with Newton's picture. For one thing, his theory required gravity to act instantaneously across any distance. If the sun suddenly vanished, Newton's theory said Earth would immediately fly off in a straight line, feeling the loss of the sun's gravitational pull the instant it disappeared. But this instantaneous action at a distance troubled many physicists, including Einstein. How could one object affect another instantly across millions of miles of empty space? What was the mechanism? Newton himself admitted he had no answer to these questions. Einstein approached the problem from a completely different angle. Instead of thinking of gravity as a force, he imagined it as a consequence of the geometry of space and time. In Einstein's picture, massive objects don't pull on each other through empty space. Instead, they curve the space around them, and objects moving through that curved space follow the straightest possible paths, which happen to be curved. It's like rolling a marble across a stretched rubber sheet. If you place a heavy ball in the center of the sheet, it creates a depression. A marble rolling past will curve around that depression, not because the heavy ball is pulling on it with some mysterious force, but simply because it's following the geometry of the curved surface. But Einstein went further than just curved space. He realized that time is also part of the geometry that gets curved by mass and energy. Space and time aren't separate things, but are woven together into a four-dimensional fabric called spacetime. And this spacetime isn't just a passive backdrop for the universe's events. It's dynamic, capable of being bent, twisted, and yes, rippled. The mathematics of general relativity are notoriously complex. Einstein's field equations, which describe how matter and energy curve spacetime, are a set of 10 coupled nonlinear partial differential equations. Solving them exactly is possible only in the simplest situations. But within these equations, Einstein found something remarkable. Just as Maxwell's equations of electromagnetism predict that accelerating electric charges create electromagnetic waves, light waves, Einstein's equations predicted that accelerating masses should create waves in spacetime itself. Think about what this means. When you wave your hand, you're actually creating gravitational waves. The mass of your hand is accelerating, and according to general relativity, this must send ripples through spacetime. Of course, these waves are so incredibly weak that we could never hope to detect them. The gravitational waves from your waving hand are many, many orders of magnitude weaker than even our most sensitive instruments could ever measure. But the principle is there. Accelerating mass disturbs spacetime, and that disturbance propagates outward as a wave. Einstein first wrote about gravitational waves in 1916, just months after publishing general relativity. In a paper submitted to the Prussian Academy of Sciences, he showed that his equations predicted the existence of 3 types of waves. However, he made an error in his calculations, and one of the wave types he predicted doesn't actually exist. It wasn't until 1918 that he published a corrected version, showing that gravitational waves come in 2 polarizations, stretching space in one direction while squeezing it in the perpendicular direction. But here's where the story takes an interesting turn. Despite predicting gravitational waves, Einstein wasn't convinced they were real physical phenomena. He thought they might be mathematical artifacts, coordinate effects that would disappear if you chose the right reference frame. This wasn't an unreasonable concern. General relativity is full of coordinate-dependent effects that don't represent physical reality. The question was whether gravitational waves were among them. Einstein's doubts were so strong that in 1936, 20 years after his original prediction, he submitted a paper with his assistant Nathan Rosen, claiming to prove that gravitational waves didn't exist. The paper was sent to the Physical Review, where it was rejected after peer review. The reviewer, who remained anonymous but was likely the cosmologist Howard Percy Robertson, had found an error in Einstein and Rosen's argument. Einstein was furious about the rejection. He wasn't used to having his papers peer-reviewed. But eventually he recognized the error and reversed his position. Gravitational waves, he concluded, were real after all. Part of what made gravitational waves so difficult to accept was their incredible weakness. Gravity is by far the weakest of the 4 fundamental forces. The electromagnetic force between 2 protons is about 10 to the 36th power, times stronger than their gravitational attraction. This means that gravitational waves carry very little energy compared to electromagnetic waves. A gravitational wave strong enough to detectably stretch and squeeze space would require incredibly massive objects undergoing incredible accelerations. Einstein calculated that even the most powerful sources he could imagine, binary star systems where 2 stars orbit each other, would produce gravitational waves so weak that detecting them would be practically impossible. He wrote that gravitational waves would never play a role in practice. This wasn't pessimism so much as realism given the technology of his time. The effects he was predicting were so small that they seemed forever beyond the reach of experimental verification. To understand just how weak gravitational waves are, consider this. A typical gravitational wave passing through Earth might stretch a kilometre-long ruler by less than the width of a proton. That's a change of about 1 part in 10 to the 21st power. Detecting such a tiny effect would require measuring distances with a precision that seemed impossible in Einstein's time and for many decades after. But the theoretical implications of gravitational waves were profound, regardless of whether they could be detected. For one thing, they resolved a major issue with general relativity's consistency with special relativity. Special relativity says nothing can travel faster than light, including information. If gravitational waves exist and travel at the speed of light, then gravity respects this cosmic speed limit. Changes in a gravitational field propagate outward at light speed, just as changes in an electromagnetic field do. Gravitational waves also carry energy away from their sources. This might seem like a trivial point, but it has important consequences. A binary system of 2 stars orbiting each other is constantly producing gravitational waves. These waves carry away energy, which must come from somewhere. The only source is the orbital energy of the system itself. This means the two stars must slowly spiral toward each other as gravitational waves drain their orbital energy. The effect is tiny for most binary systems, but it's there, a slow decay that would eventually cause any orbiting objects to merge. The mathematical structure of gravitational waves reveals something beautiful about the nature of space-time. Unlike electromagnetic waves, which can have various patterns depending on their source, gravitational waves have a very specific structure. They're quadrupole waves, meaning they stretch space in one direction while compressing it in the perpendicular direction, then reverse, creating a characteristic plus and cross pattern. This pattern is a direct consequence of the geometry of space-time and the fact that gravity is always attractive, never repulsive. As Einstein worked through the mathematics, he discovered that gravitational waves couldn't be produced by spherically symmetric motion. A perfectly spherical star collapsing or exploding wouldn't produce gravitational waves no matter how violent the event. You need a symmetric motion, acceleration that changes the quadrupole moment of the mass distribution. This is why binary systems are such good sources. Two masses orbiting each other create exactly the kind of asymmetric acceleration needed to generate strong gravitational waves. Einstein also realized that gravitational waves would be incredibly penetrating. Unlike light, which can be absorbed or scattered by matter, gravitational waves pass through almost everything essentially unchanged. A gravitational wave could pass through the entire Earth and emerge on the other side having lost virtually none of its strength. This makes them both incredibly difficult to detect, since they barely interact with our detectors, and incredibly valuable as astronomical messengers, since they can bring us information from regions opaque to light. The prediction of gravitational waves was both a triumph and a frustration for Einstein. It was a triumph because it emerged naturally from his theory, a necessary consequence of the mathematics rather than something added by hand. The existence of gravitational waves follows inevitably from two simple facts. Space-time can be curved by mass and energy, and changes in that curvature propagate at a finite speed. Given these premises, gravitational waves must exist. But it was also a frustration because Einstein knew he would never see them detected. The technology simply didn't exist, and he couldn't imagine how it ever would. In his later years, he seems to have regarded gravitational waves as an interesting theoretical curiosity, a prediction of his theory that would forever remain in the realm of pure mathematics rather than experimental physics. What Einstein couldn't have foreseen was the incredible technological progress that would occur in the decades after his death. He couldn't have imagined lasers, computers, or the level of precision that modern engineering would achieve. He couldn't have known that binary systems far more extreme than any he considered would be discovered. Systems where neutron stars and black holes spiral together, creating gravitational waves billions of times stronger than those from ordinary stars. After Einstein's prediction, gravitational waves entered a strange twilight period in physics. They existed in the equations, elegant and undeniable in their mathematical form, but seemed forever beyond the reach of experimental verification. For decades, physicists debated whether these waves were real physical phenomena or merely mathematical artifacts, coordinate illusions that appeared in the equations but had no actual physical significance. This period of doubt and gradual acceptance would stretch for nearly half a century, filled with theoretical arguments, thought experiments, and slowly building conviction that Einstein's waves were real. The confusion wasn't helped by the fact that some of the greatest minds in physics kept changing their positions. Einstein himself, as we've seen, went from predicting gravitational waves to denying them to accepting them again. Other prominent physicists were equally uncertain. The great British astrophysicist Arthur Eddington, who had helped confirm general relativity by measuring the bending of starlight during a solar eclipse, was skeptical about gravitational waves. He joked that they travelled at the speed of thought, suggesting they were merely artifacts of how physicists chose to think about the problem rather than real physical phenomena. Part of the difficulty was that general relativity allows for tremendous freedom in choosing coordinates. You can describe space-time using many different coordinate systems, just as you can describe Earth's surface using latitude and longitude, or completely different coordinate schemes. Some things that appear to be physical effects in one coordinate system disappear when you transform to another. The challenge was determining whether gravitational waves were coordinate independent, whether they represented real physical effects that would exist regardless of how you chose to describe space-time. The debate took on an almost philosophical character. What does it mean for something to be real in physics? If gravitational waves carried energy, if they could do work, if they could be detected in principle, even if not in practice, then surely they must be real. But proving that gravitational waves carried energy turned out to be surprisingly subtle. The energy density of a gravitational wave can't be localized to a specific point in space the way electromagnetic energy can. Instead, it's a kind of averaged effect, visible only when you look at regions larger than the wavelength of the wave. A breakthrough in understanding came from Hermann Bondi, a British-Austrian physicist who would later become famous for his work on cosmology. In 1957, Bondi organized a conference at Chapel Hill, North Carolina, specifically to address the reality of gravitational waves. At this conference, Richard Feynman, the brilliant American physicist known for his work in quantum mechanics, presented a simple thought experiment that would become known as the sticky bead argument. Feynman imagined a stick with beads that could slide along it freely, with just a tiny bit of friction. If a gravitational wave passed by, it would alternately stretch and squeeze space. The stick and beads would be affected slightly differently because they're separate objects. This would cause the beads to slide back and forth along the stick. The friction would generate heat, meaning the gravitational wave had done work, had transferred energy to the system. If gravitational waves could heat up a stick with beads, Feynman argued, they must be real physical phenomena, not just mathematical conveniences. This simple argument was surprisingly powerful. It cut through the mathematical complexity and coordinate confusion to focus on a simple physical effect. The sticky bead argument convinced many physicists that gravitational waves were real, though some skeptics remained. The debate wouldn't be fully settled until gravitational waves were actually detected, but Feynman's argument marked a turning point in how the physics community thought about them. Meanwhile, another development was building confidence in gravitational waves. Joseph Weber, an American physicist at the University of Maryland, had begun thinking seriously about how to detect them. Weber was an interesting character, a former naval officer who had worked on microwave radar during World War II before turning to physics. In the late 1950s, he started calculating whether it might be possible to build a detector sensitive enough to measure gravitational waves. Weber's calculations were encouraging, or at least not entirely discouraging. He figured that while gravitational waves from binary star systems would be far too weak to detect, more violent events might produce detectable waves. Supernovae, the explosive deaths of massive stars, could potentially produce strong enough waves if they happened close enough to Earth. The key insight was that you didn't need to detect the tiny waves Einstein had calculated from ordinary binary stars. You could wait for rare, catastrophic events that would produce much stronger waves. In 1960, Weber built the first gravitational wave detector, a massive aluminum cylinder weighing about a ton. The idea was that a passing gravitational wave would cause the cylinder to ring like a bell, vibrating at its resonant frequency. Sensitive piezoelectric sensors attached to the cylinder would detect these vibrations. Weber called these devices resonant bar detectors, and they represented humanity's first serious attempt to detect gravitational waves. Weber's bars were engineering marvels for their time. He had to isolate them from all sources of vibration, including seismic activity, thermal noise, and even the vibrations from nearby traffic. He suspended the bars in vacuum chambers, cooled them to reduce thermal noise, and developed sophisticated filtering techniques to separate potential gravitational wave signals from noise. It was pioneering work that established many of the techniques that would be used in all future gravitational wave detectors. In 1969, Weber made an announcement that electrified the physics community. He claimed to have detected gravitational waves. His two detectors, one in Maryland and one near Chicago, had registered coincident events, vibrations that occurred at the same time in both detectors. Since the detectors were separated by hundreds of miles, Local disturbances couldn't explain the coincidences. Weber argued that he was seeing gravitational waves, probably from supernovae or other catastrophic events in our galaxy. The physics community was initially excited but also cautious. If Weber was right, it would be the discovery of the century, the first direct detection of gravitational waves and confirmation of one of general relativity's most exotic predictions. Other groups quickly built their own bar detectors, trying to replicate Weber's results. But as more and more groups searched for gravitational waves, they found nothing. No one could reproduce Weber's claimed detections. The situation became increasingly awkward as the 1970s progressed. Weber continued to claim detections, even improving his apparatus and finding more events, but no other group saw anything. Detailed analyses of Weber's data suggested that he was misinterpreting statistical fluctuations as real signals. The rate at which Weber claimed to be detecting gravitational waves implied that our galaxy was converting mass to gravitational wave energy at an impossible rate, losing the equivalent of thousands of suns per year. The galaxy would have been completely disrupted long ago if Weber's detection rate was real. By the late 1970s, the consensus was clear. Weber hadn't detected gravitational waves. His results were some combination of statistical error, wishful thinking, and possibly unconscious bias in data analysis. It was a painful episode for the field, and particularly for Weber, who went to his grave in 2000 believing he had detected gravitational waves. But Weber's work, even though it didn't detect real gravitational waves, was invaluable. He showed that detection might be possible, pioneered many important techniques, and inspired a generation of physicists to think seriously about gravitational wave detection. While the experimental efforts were struggling, theoretical understanding of gravitational waves was advancing rapidly. In the 1960s, physicists began to understand what kinds of sources might produce detectable gravitational waves. The key insight was that you needed extremely massive objects moving at speeds close to the speed of light. Ordinary stars, even in binary systems, just didn't have enough mass or move fast enough to produce strong waves. But what about more exotic objects? In the 1960s, neutron stars were discovered. City-sized remnants of dead stars with masses greater than the Sun compressed into a sphere just 20 kilometers across. These objects were so dense that their gravity could accelerate material to significant fractions of the speed of light. A binary system of two neutron stars spiraling together would produce gravitational waves far stronger than anything Einstein had imagined. Black holes were even more promising. These regions of spacetime where gravity is so strong that nothing can escape were predicted by general relativity, but seemed so exotic that many physicists doubted they existed. But in the 1960s and 70s, increasingly strong evidence suggested that black holes were real. And if they were real, then black hole mergers would produce the strongest gravitational waves possible, waves that might be detectable even from billions of light-years away. Russell Hulse and Joseph Taylor made a crucial discovery in 1974 that would finally provide indirect evidence for gravitational waves. Using the Arecibo radio telescope in Puerto Rico, they discovered a pulsar, a rapidly rotating neutron star, in a binary system with another neutron star. This system, known as the Hulse-Taylor binary, was perfect for testing general relativity's predictions about gravitational waves. The two neutron stars orbit each other every 7 3/4 hours, moving at speeds of about 300 kilometers per second. According to general relativity, this system should be producing gravitational waves, losing energy, and slowly spiraling inward. Hulse and Taylor could measure the orbital period of the system with extraordinary precision by timing the pulsar's radio pulses. Over several years, they watched the orbital period decrease by about 76 microseconds per year, exactly what general relativity predicted if the system was losing energy to gravitational waves. This was a triumph. While it wasn't direct detection of gravitational waves, it was powerful indirect evidence that they existed and behaved exactly as Einstein's theory predicted. Hulse and Taylor won the Nobel Prize in Physics in 1993 for this discovery. Their work convinced even the remaining skeptics that gravitational waves were real. The question was no longer whether gravitational waves existed, but whether we could ever detect them directly. The Hulse-Taylor binary also gave physicists a better understanding of what they were looking for. The gravitational waves from the system were far too weak to detect directly with any conceivable technology, but the system would continue spiraling inward, and in about 300 million years the two neutron stars would merge. In those final moments, as the neutron stars plunged together at speeds approaching the speed of the light, they would produce a burst of gravitational waves that would be among the strongest in the universe. This realization shifted the focus of gravitational wave detection. Instead of looking for continuous waves from binary systems or hoping to catch nearby supernovae, physicists began to think about detecting the mergers of compact objects like neutron stars and black holes. These events would be rare, perhaps a few per year in our galaxy, but they would produce waves strong enough to detect from much farther away. If you could build a detector sensitive enough, you could monitor millions or billions of galaxies, making detection of these rare events feasible. To truly understand gravitational waves, we need to step back and examine the stage on which they perform, the remarkable structure we call spacetime. This isn't just empty space with objects moving through it. It's a dynamic four-dimensional fabric that can bend, twist, stretch, and ripple. Understanding spacetime is like learning the language in which gravitational waves speak, and once you understand this language, the existence of these waves seems not just possible, but inevitable. Let's start with something that might seem simple, but is actually quite profound. What do we mean when we say space and time are united into spacetime? In our everyday experience, space and time feel completely different. Space is where things are, the three dimensions of up, down, left, right, forward, backward that we navigate every day. Time is when things happen, the steady flow from past through present to future. They seem like fundamentally different categories of existence. But Einstein's special relativity, published in 1905, showed that space and time are more intimately connected than we realized. The key insight was that different observers, moving at different velocities, disagree about distances and durations. What one observer sees as purely spatial separation, another observer, moving at a different speed, sees as a mixture of spatial and temporal separation. Space and time aren't absolute stages, but are relative, depending on the motion of the observer. This led to the concept of space-time, a four-dimensional continuum where events are located not just in space, but in time as well. Every event, whether it's a star exploding, a flower blooming, or you reading these words, has 4 coordinates, 3 for its spatial location and 1 for when it occurs. The geometry of space-time determines how these events are related, which can influence each other, and how information and causality flow through the universe. In special relativity, space-time is flat, like a 4-dimensional version of a perfectly smooth table. Objects move through this flat space-time in straight lines unless acted upon by forces, but general relativity introduced a revolutionary idea: mass and energy curve space-time. The presence of a massive object like a star or planet distorts the geometry of space-time around it, and this distortion is what we experience as gravity. Imagine space-time as a stretched rubber sheet, though remember this is just an analogy, and the real 4-dimensional space-time is far more complex. Place a bowling ball on the sheet and it creates a depression. Roll marbles near the bowling ball and they curve around the depression. That's roughly how mass curves space-time and how that curvature affects the motion of other objects. But unlike the rubber sheet, which curves in space, space-time curvature involves both space and time dimensions in ways our everyday intuition struggles to grasp. The curvature of space-time isn't just a mathematical abstraction. It has real, measurable effects. Clocks run slower in stronger gravitational fields, an effect called gravitational time dilation. GPS satellites have to account for this effect. Their clocks run faster than clocks on Earth's surface because they are in a weaker gravitational field. Without corrections for general relativity, GPS would accumulate errors of about 10 kilometers per day. Light itself follows the curvature of space-time. When light from a distant star passes near the Sun's gravitational field, which is really the curvature of space-time near the Sun, bends the light's path. This gravitational lensing effect was one of the first confirmations of general relativity, and is now a powerful tool for studying distant galaxies and dark matter. Now here's where gravitational waves enter the picture. If space-time can be curved by mass and energy, what happens when massive objects accelerate? The curvature must change, and that change can't happen instantaneously everywhere. Just as accelerating electric charges create electromagnetic waves, accelerating masses create ripples in the curvature of space-time. These ripples propagate outward at the speed of light, carrying information about the changing gravitational field. But gravitational waves aren't like waves on water or sound waves in air. Those waves need a medium to propagate through. Gravitational waves are distortions in space-time itself. They don't move through space, they are moving distortions of space. When a gravitational wave passes by, it literally stretches and squeezes the distances between objects. If you had a perfect ruler and tried to measure the wave, you'd find that the ruler itself stretches and squeezes along with the space it's measuring. This is what makes gravitational waves so difficult to detect. Every physical object, every measuring device, is embedded in space-time and affected by its distortions. It's like trying to measure ocean waves while floating in the water. You rise and fall with the waves, making it hard to detect the wave's passage. The key to detecting gravitational waves is finding some way to compare distances or times that are affected differently by the passing wave. The specific pattern of stretching and squeezing in a gravitational wave is determined by the nature of gravity itself. Unlike electromagnetic forces, which can be either attractive or repulsive, gravity is always attractive. This fundamental difference gives gravitational waves their characteristic quadrupole pattern. As a wave passes through, it stretches space in one direction, while simultaneously squeezing it in the perpendicular direction, then reverses the pattern. Imagine a ring of particles floating in space. As a gravitational wave passes through the ring, traveling perpendicular to its plane, the ring distorts into an ellipse, first stretched horizontally and squeezed vertically, then stretched vertically and squeezed horizontally, oscillating back and forth. This is the signature pattern of a gravitational wave, and it's the same regardless of what created the wave, whether it was colliding black holes, merging neutron stars, or any other source. The strength of a gravitational wave decreases with distance from its source, but in a very specific way. The amplitude of the wave, which measures how much it stretches and squeezes space, decreases inversely with distance. This is different from electromagnetic waves, whose intensity decreases with the square of distance. This means gravitational waves maintain their coherence over vast distances better than light does, though they're also much weaker to begin with. One of the most remarkable properties of gravitational waves is their ability to pass through matter essentially unimpeded. While light can be absorbed, scattered, or blocked by intervening material, gravitational waves sail through almost as if the matter weren't there. A gravitational wave could pass through the entire Earth and emerge virtually unchanged. This makes them incredibly valuable as astronomical messengers, able to bring us information from regions completely opaque to electromagnetic radiation. This transparency to matter comes from the fundamental weakness of gravity compared to other forces. The gravitational interaction between a passing gravitational wave and the atoms in a solid object is so weak that the wave passes through with negligible absorption or scattering. It's estimated that a gravitational wave would have to travel through a solid lead wall several light-years thick before losing half its amplitude. For comparison, visible light can't penetrate even a thin sheet of metal. The frequency of gravitational waves tells us about their sources. Just as sound waves have different pitches depending on what creates them, gravitational waves come in different frequencies depending on their origins. The gravitational waves from binary black holes merging have frequencies in the range of tens to thousands of hertz, similar to the frequencies of sound waves we can hear. The waves from binary neutron stars are similar but slightly higher in pitch. Supermassive black holes in the centers of galaxies create much lower frequency waves, taking minutes or hours for each oscillation. And the gravitational waves from the early universe, if they exist, would have even lower frequencies, with periods of years or longer. The energy carried by gravitational waves is enormous by everyday standards, but tiny compared to the total energy involved in their creation. When two black holes merge, they can convert several solar masses worth of matter into gravitational wave energy, according to Einstein's famous equation E=mc². That's more energy than all the stars in the observable universe emit in light during the same brief period. Yet this tremendous energy is spread out over an enormous volume of space by the time the waves reach us, making them incredibly difficult to detect. Understanding how spacetime can carry waves also helps us understand one of the most profound aspects of general relativity. Spacetime isn't just a passive arena where events occur. It's a dynamic entity that can store and transmit information. When massive objects accelerate in distant galaxies, they create ripples that carry information about those events across the universe. These ripples travel for millions or billions of years, preserving a record of ancient catastrophes until they finally wash over our detectors. The mathematics describing how gravitational waves propagate through spacetime is beautiful but complex. Einstein's field equations, which relate the curvature of spacetime to the energy and momentum within it, are nonlinear. This means that gravitational waves can, in principle, interact with each other, though this effect is so weak it's never been observed and likely never will be. It also means that very strong gravitational waves could create their own additional curvature, though again, this effect is negligible for any waves we could hope to detect. What's particularly elegant about gravitational waves is that they're a necessary consequence of two simple principles. First, spacetime can be curved by mass and energy. Second, changes in this curvature propagate at a finite speed, the speed of light. Given these two facts, gravitational waves must exist. If changes in gravity propagated instantaneously, there would be no waves. If spacetime couldn't be curved, there would be nothing to wave. But with both properties, waves are inevitable. The speed of gravitational waves is particularly important. They travel at exactly the speed of light, not approximately, but exactly. This isn't a coincidence. Both light and gravitational waves travel at the fundamental speed limit of the universe, the speed at which causality itself propagates. This speed, roughly 300,000 kilometers per second, is built into the structure of spacetime itself. It's the conversion factor between space and time, the speed at which cause and effect ripple through the universe. This connection between gravitational waves and the speed of light was beautifully confirmed in 2017, when astronomers detected both gravitational waves and light from the same event, the merger of two neutron stars. The gravitational waves and the gamma rays arrived within 2 seconds of each other after travelling for 130 million years. This incredible agreement, better than 1 part in 10 to the 15th, confirmed that gravitational waves do indeed travel at the speed of light. The fact that spacetime can ripple also tells us something profound about the nature of gravity. In Newton's theory, gravity was a force acting between objects. In general relativity, gravity is the curvature of spacetime. But if spacetime can carry waves, if it can oscillate and transmit energy, then it's clearly something more than just abstract geometry. Spacetime is as real and physical as any field in nature. It can be excited, it can vibrate, and it can carry energy and information across the cosmos. This view of spacetime as a dynamic physical entity rather than just empty nothingness represents one of the most profound shifts in our understanding of the universe. The vacuum of space isn't empty, but is filled with the rich geometry of spacetime itself. Even in the absence of any matter or energy, spacetime can still ripple with gravitational waves, carrying messages from distant cosmic events. As we've built better instruments and detected more gravitational waves, we've begun to map the dynamic behavior of spacetime itself. Each detection tells us about how spacetime responds to extreme conditions, how it vibrates when struck by cosmic catastrophes, and how it carries information across billions of light years. We're learning to read the tremors in the fabric of reality itself. The architecture of spacetime also determines what kinds of gravitational waves are possible. Not every motion creates gravitational waves. A perfectly spherical star pulsating in and out wouldn't create any waves, no matter how violently it pulsated. You need a symmetric motion, specifically changes in the quadrupole moment of the mass distribution. This is why binary systems are such good sources. Two masses orbiting each other create exactly the kind of asymmetric, time-varying gravitational field needed to generate strong waves. The way spacetime responds to passing gravitational waves also depends on the local environment. In principle, a strong gravitational field could focus or defocus gravitational waves, similar to how a lens focuses light. Gravitational waves passing near massive objects could be gravitationally lensed, creating multiple images or amplifying the signal. While this hasn't been observed yet, it's predicted by general relativity, and could provide another tool for studying both gravitational waves and the massive objects that lens them. In the vast darkness between the stars, cosmic giants dance their final spirals, locked in gravitational embraces that will end in violent merger. These binary systems, pairs of neutron stars, black holes, or one of each, are the universe's most powerful gravitational wave sources, converting enormous amounts of energy into ripples in spacetime during their final moments together. Understanding these systems, how they form, how they evolve, and how they ultimately merge, is crucial to understanding the gravitational waves we detect. Let's begin with the dancers themselves. Neutron stars are among the universe's most extreme objects, the crushed cores of massive stars that exploded as supernovae. When a star much more massive than our Sun exhausts its nuclear fuel, it can no longer support itself against its own gravity. The outer layers explode outward in a supernova, while the core collapses inward. If the core is between about 1 and 3 solar masses, it becomes a neutron star, an object so dense that a teaspoon of its material would weigh about as much as Mount Everest. Neutron stars are typically about 20 kilometers in diameter, but contain more mass than our Sun. The gravity at their surface is about 200 billion times stronger than Earth's gravity. Their density is so extreme that atomic nuclei are crushed together, forming a soup of neutrons with perhaps a seasoning of other exotic particles. The physics of neutron star interiors pushes our understanding to its limits, involving quantum mechanics, nuclear physics, and general relativity all at once. Many neutron stars are pulsars, rapidly rotating objects that emit beams of radiation from their magnetic poles. As these beams sweep past Earth like lighthouse beacons, we see regular pulses of radio waves, optical light, or even gamma rays. Some pulsars spin hundreds of times per second, their surfaces moving at significant fractions of the speed of light. The magnetic fields of neutron stars can be 1 trillion times stronger than Earth's magnetic field, so strong that they would rip the iron from your blood from 1,000 kilometers away. Black holes are even more extreme. These are regions where gravity has won completely, where matter has collapsed past the point of no return. The boundary of a black hole, called the event horizon, marks the point beyond which nothing can escape, not even light. Inside the event horizon, all paths lead inexorably to the singularity at the center, where our current understanding of physics breaks down. Black holes come in various sizes. Stellar mass black holes formed from the collapse of massive stars typically have masses between about 3 and 20 times the mass of our Sun. Supermassive black holes found at the centers of galaxies can have masses millions or billions of times greater than our Sun. There might also be intermediate mass black holes, though these remain somewhat mysterious, and primordial black holes formed in the early universe, though none have been definitively detected. Despite their name, black holes aren't perfectly black. Stephen Hawking showed that quantum effects near the event horizon cause black holes to emit radiation, now called Hawking radiation. However, this radiation is incredibly weak for astronomical black holes, far too faint to detect. A black hole with the mass of our Sun would take 10 to the 67th years to evaporate through Hawking radiation, many times longer than the current age of the universe. Now imagine 2 of these extreme objects locked in a gravitational dance. Binary systems containing neutron stars or black holes can form in several ways. 2 massive stars might be born together in a binary system, both eventually collapsing to form compact objects. Alternatively, 2 compact objects might capture each other through gravitational interactions in dense stellar environments like globular clusters. However they form, once 2 compact objects are gravitationally bound, their fate is sealed. As these objects orbit each other, they create a time-varying gravitational field that generates gravitational waves. The waves carry away energy and angular momentum from the system, causing the orbit to decay. The two objects spiral slowly inward, their orbital period decreasing as they get closer together. This process, called gravitational wave in spiral, can take millions or billions of years for widely separated objects. The mathematics of this inspiral is elegant and precise. For two objects in a circular orbit, the rate of energy lost to gravitational waves depends on their masses, their separation, and their orbital frequency. More massive objects produce stronger waves. Closer objects moving faster produce much stronger waves, with the power radiated increasing as the orbital frequency to the 10/3 power. This strong dependence on frequency means that the waves get much stronger as the objects spiral closer together. For most of their inspiral, the two objects move relatively slowly compared to the speed of light, and Newton's laws with small relativistic corrections accurately describe their motion. But as they get closer, moving faster, relativistic effects become increasingly important. The objects begin to move at significant fractions of the speed of light. Spacetime curvature becomes extreme, and the full machinery of general relativity is needed to describe what happens. The final stage of the inspiral is spectacular. In the last few seconds before merger, two stellar mass black holes might orbit each other hundreds of times per second, moving at speeds approaching the speed of light. The gravitational waves during this phase are enormous, carrying away energy at a rate greater than the luminosity of all the stars in the observable universe combined. Space itself rings like a struck bell as these titans spiral together. When neutron stars are involved, the situation becomes even more complex. Unlike black holes, which are essentially pure gravity, neutron stars are made of matter. As two neutron stars spiral together, tidal forces, the same forces that cause ocean tides on Earth but enormously stronger, begin to distort the stars. They stretch toward each other, possibly shedding material that forms an accretion disk around the system. If the neutron stars get close enough before merging, they can actually rip each other apart through tidal forces. The neutron star material, freed from the crushing gravity that confined it, expands explosively. Nuclear reactions in this expanding material can create heavy elements like gold, platinum, and uranium through a process called R-process nucleosynthesis. A single neutron star merger can produce several Earth masses of gold, along with other heavy elements. The merger itself is a moment of extreme physics. For black holes, the two event horizons touch and merge into one, forming a single larger black hole. This new black hole is initially highly distorted, ringing down to a stable state by emitting gravitational waves. The pattern of this ring down, like the sound of a struck bell, depends on the mass and spin of the final black hole, providing a test of general relativity in the strong field regime. For neutron star mergers, the outcome depends on the total mass. If the combined mass is below a certain threshold, about 2.5 to 3 solar masses, though the exact value depends on the equation of state of neutron star matter, the merger produces a hypermassive neutron star. This object is temporarily supported by rapid rotation, but will eventually collapse to a black hole. If the total mass is above the threshold, the merger immediately produces a black hole. The matter dynamics in neutron star mergers are incredibly complex. Temperatures reach billions of degrees, densities exceed nuclear density, and magnetic fields of enormous strength are generated and amplified. Neutrinos stream out in vast numbers, carrying away energy. Jets of material might be launched at speeds approaching the speed of light. All of this happens in a fraction of a second, making neutron star mergers among the most violent events in the universe. These mergers don't just produce gravitational waves. They're also sources of electromagnetic radiation across the entire spectrum. The radioactive decay of newly formed heavy elements powers a kilonova, an optical and infrared transient that can shine for days or weeks. If jets are launched, they can produce short gamma-ray bursts, brief flashes of the most energetic form of light. The merger might also produce radio emission as ejected material interacts with the surrounding environment. The gravitational waves from these mergers carry detailed information about the objects involved. The frequency and amplitude of the waves during the inspiral phase tell us about the masses of the two objects. The way the frequency changes over time reveals their orbital dynamics. For neutron stars, subtle features in the gravitational wave signal can reveal information about their internal structure, the equation of state of matter at nuclear densities. The merger and ring-down phases are particularly rich in information. The exact gravitational wave signal during merger depends on the masses, spins, and, for neutron stars, the internal structure of the merging objects. The ring-down of the final black hole has characteristic frequencies and damping times that depend only on its mass and spin, providing a clean test of general relativity's predictions for black holes. Binary systems of compact objects are distributed throughout the universe, though they're rare enough that detecting their mergers requires monitoring enormous volumes of space. Current gravitational wave detectors can detect stellar mass black hole mergers from billions of light-years away, encompassing millions of galaxies. Even with such enormous search volumes, these events are rare, perhaps a few dozen per year that are close enough and favorably oriented for detection. The distribution and properties of these binary systems tell us about stellar evolution, the dynamics of dense stellar systems, and the history of star formation in the universe. Each detection adds to our census of compact objects, revealing black holes more massive than we expected, neutron stars at the limits of what matter can support, and systems that challenge our understanding of how such binaries form and evolve. As our gravitational wave detectors improve, we're discovering an increasingly rich population of compact object binaries. We've seen black holes from just a few solar masses to nearly 100 solar masses. We've detected neutron stars near the minimum mass for neutron star formation, and others pushing against the maximum mass before collapse to a black hole. We've even seen mixed systems, a neutron star spiraling into a black hole, each type of system producing its own characteristic gravitational wave signature. The journey from Einstein's theoretical prediction to the actual detection of gravitational waves spans nearly a century of human ingenuity, technological advancement, and sheer determination. This quest pushed the boundaries of what seemed possible, requiring measurements of such exquisite precision that many physicists thought detection would forever remain beyond our reach. The story of how we learned to hear the universe's gravitational whispers is one of the great scientific adventures of our time. After Joseph Weber's pioneering but ultimately unsuccessful attempts in the 1960s and 70s, the field of gravitational wave detection entered a period of reflection and regrouping. Weber's bar detectors, despite their sophistication for the time, simply weren't sensitive enough to detect the gravitational waves actually reaching Earth. The physics community had learned a hard lesson about the difficulty of the challenge they faced. The fundamental problem was the incredible weakness of gravitational waves. Even the most violent cosmic events produce waves that, by the time they reach Earth, cause distortions smaller than atomic nuclei. Detecting such tiny effects requires not just sensitive instruments, but also ways to distinguish real signals from the countless sources of noise that can mimic gravitational waves. Every passing truck, every minor earthquake, every fluctuation in temperature creates vibrations that dwarf the effects of gravitational waves. In the 1970s, a new approach began to take shape. Rather than trying to detect the ringing of solid bars, physicists began to consider using laser interferometry. The basic idea was elegant. Split a laser beam and send the two halves down perpendicular arms. When the beams return and recombine, they create an interference pattern that depends on the precise length of each arm. If a gravitational wave passes through, stretching one arm while squeezing the other, the interference pattern changes. The potential advantages of interferometry were enormous. Unlike bar detectors, which were most sensitive to gravitational waves at their resonant frequency, interferometers could detect waves across a broad range of frequencies. They could also, in principle, be made arbitrarily long, and longer arms meant larger changes in length for the same gravitational wave amplitude. But the technical challenges were daunting. Rainer Weiss at MIT was one of the pioneers of gravitational wave interferometry. In 1972, he wrote a paper analysing in detail the noise sources that would affect an interferometric detector and how they might be overcome. Thermal vibrations, seismic noise, quantum fluctuations in the laser light, and dozens of other effects would all need to be controlled to levels that seemed impossible with existing technology. Around the same time, groups in Germany, Britain and Scotland were also exploring interferometric detection. Heinz Billing and colleagues at the Max Planck Institute were building small prototype interferometers. Ronald Drever in Scotland was developing new techniques for stabilizing lasers and controlling noise. These early efforts were modest in scale but crucial for developing the technologies that would eventually make detection possible. The 1980s saw the birth of what would become LIGO, the Laser Interferometer Gravitational Wave Observatory. Weiss at MIT and Drever, who had moved to Caltech along with Kip Thorne, also at Caltech, became the project's founding fathers. They proposed building kilometre-scale interferometers, far larger than anything attempted before. The scale was necessary because gravitational waves cause fractional length changes. A longer baseline means a larger absolute change in length, making detection more feasible. But even kilometre-scale arms weren't enough. The team developed a clever solution called Fabry-Perot cavities. By adding mirrors at both ends of each arm, they could bounce the laser light back and forth hundreds of times before it recombined. This effectively multiplied the arm length, increasing the sensitivity to gravitational waves. A 4-kilometre arm with light bouncing back and forth could act like an arm hundreds of kilometres long. The technological requirements were staggering. The mirrors had to be polished to almost atomic smoothness. They needed to be suspended in ways that isolated them from ground vibrations, requiring sophisticated multi-stage pendulum systems. The entire light path had to be in an ultra-high vacuum to prevent air molecules from scattering the laser light. The laser itself needed to be extraordinarily stable in both frequency and intensity. Seismic isolation presented particular challenges. Ground vibrations from sources as distant as ocean waves crashing on beaches thousands of kilometers away could overwhelm gravitational wave signals. The team developed both passive and active isolation systems. Passive systems used masses and springs to filter out vibrations. Active systems used sensors and actuators to actively cancel out detected motion, similar to noise-cancelling headphones but for seismic waves. The mirrors themselves became masterpieces of engineering. Made from ultra-pure fused silica, they were polished to tolerances of less than a nanometer. Special coatings were developed that would reflect the laser light almost perfectly while minimizing thermal noise. The mirrors were suspended by glass fibers thinner than human hair, chosen because glass has very low mechanical loss, meaning vibrations die out quickly rather than persisting as noise. Quantum mechanics posed another fundamental limit. The Heisenberg uncertainty principle says you can't simultaneously know both the position and momentum of a particle with perfect precision. For the photons in LIGO's laser beam, this translates to uncertainty in the measured position of the mirrors. This quantum noise would ultimately limit LIGO's sensitivity, but reaching this quantum limit required eliminating all other sources of noise first. The control systems for LIGO were incredibly complex. Hundreds of feedback loops kept the mirrors aligned, the laser frequency stable, and the interferometer operating at its most sensitive point. These systems had to respond to disturbances in microseconds while remaining stable over hours of operation. The computing power required to analyze the data in real time was substantial, requiring custom-built electronics and sophisticated algorithms. Initial LIGO, which operated from 2002 to 2010, was in many ways a proof of concept. It demonstrated that kilometre-scale interferometry was feasible, but wasn't quite sensitive enough to detect gravitational waves unless a source happened to be unusually close. No detections were made, but this wasn't unexpected. Initial LIGO was always intended as a stepping stone to the more sensitive advanced LIGO. During this time, other gravitational wave detectors were also being built around the world. Virgo, a 3-kilometre interferometer in Italy, began operations in 2007. GU600 in Germany, though smaller at 600 metres, served as a testbed for advanced technologies. Tama 300 in Japan pushed the boundaries of what could be achieved with a 300-metre interferometer. The international nature of gravitational wave detection was crucial. Multiple detectors in different locations could confirm that a signal was real rather than local noise. They could also triangulate the source's position on the sky, essential for follow-up observations with conventional telescopes. The gravitational wave community, once small and somewhat isolated, grew into a global collaboration. Advanced LIGO represented a quantum leap in sensitivity. Every subsystem was upgraded based on lessons learned from initial LIGO. More powerful lasers, heavier mirrors, better isolation systems, and improved coatings all contributed to a tenfold improvement in sensitivity. This meant advanced LIGO could detect sources 10 times farther away, surveying a volume of space 1,000 times larger than initial LIGO. The vacuum system for advanced LIGO was one of the largest ultra-high vacuum systems ever built. The beam tubes, 4 kilometers long and over a meter in diameter, had to be evacuated to pressures less than 1/1,000,000th of atmospheric pressure. Any residual gas molecules could scatter the laser light, creating noise that would swamp gravitational wave signals. Achieving and maintaining this vacuum required sophisticated pumping systems and careful attention to materials that might outgaze. The mirrors for advanced LIGO weighed 40 kilograms each, much heavier than initial LIGO's mirrors. This mass helped reduce the effect of quantum radiation pressure noise, the random kicks from individual photons hitting the mirrors, but suspending these heavy mirrors required new suspension systems, complex assemblies of masses and fibers that isolated the mirrors from vibrations, while allowing precise control of their positions. Signal processing and data analysis presented their own challenges. LIGO produces terabytes of data every day, streams of numbers representing the measured length difference between the arms. Hidden in this data, maybe once every few days or weeks, might be the tiny signature of a gravitational wave. Extracting these signals required sophisticated algorithms, including matched filtering, that compared the data to theoretical templates of gravitational wave signals. The computational requirements were enormous. Analyzing LIGO data required supercomputers running for months, searching through different combinations of parameters to find potential signals. Machine learning algorithms were developed to help identify and classify noise sources. The data analysis pipeline had to be robust enough to handle real-time detection, while also allowing for deeper offline searches. By 2015, advanced LIGO was ready. Years of commissioning had brought the detectors to design sensitivity. The mirrors hung motionless in their vacuum chambers, isolated from the vibrating world outside. Lasers traced their paths billions of times each second, measuring distances to a precision that seemed impossible just decades earlier. The stage was set for one of the most anticipated discoveries in physics. The decades-long quest to detect gravitational waves had transformed from a quixotic dream to a realistic possibility. Thousands of scientists and engineers had contributed to this effort, developing technologies that pushed the boundaries of what was possible. The detectors they built were among the most sensitive instruments ever created, capable of measuring changes in distance smaller than anything else humans had ever attempted to measure. The Laser Interferometer Gravitational Wave Observatory, LIGO, represents one of humanity's most audacious scientific instruments. It is a machine designed to measure distances to a precision that defies comprehension, detecting changes smaller than 1/10,000th the width of a proton. To understand how LIGO works is to appreciate the extraordinary lengths to which scientists and engineers have gone to hear the faint whispers of spacetime itself. LIGO consists of 2 identical detectors, one in Hanford, Washington, and another in Livingston, Louisiana, separated by 3,000 kilometers. This separation is crucial. A real gravitational wave will pass through both detectors, causing nearly simultaneous signals. Local disturbances from earthquakes to falling trees will affect only one detector. By requiring coincident detection, LIGO can distinguish cosmic signals from terrestrial noise. Each LIGO detector forms an enormous L shape, with arms stretching 4 kilometers in each direction. At the corner where the arms meet sits the heart of the detector, the laser source, beam splitter, and photodetector. Down each arm runs a beam tube, a stainless steel pipe over a meter in diameter, containing one of the largest vacuum systems ever created. Inside this vacuum, laser light travels back and forth, measuring the distance between mirrors with extraordinary precision. The laser itself is a marvel of stability. LIGO uses a neodymium YAG laser, producing infrared light at a wavelength of 1064 nanometers. This laser must be extraordinarily stable in both frequency and intensity. Fluctuations in laser frequency would masquerade as changes in arm length, while intensity fluctuations would create noise in the photodetector. The laser is stabilized using multiple feedback systems, keeping its frequency constant to better than 1 part in 10 to the 21st. But even this incredibly stable laser isn't powerful enough on its own. LIGO uses a series of optical cavities to build up the laser power. The first is the power recycling cavity. Light that returns from the arms and doesn't go to the photodetector is recycled back into the interferometer, building up the circulating power. This increases the effective laser power from about 200 watts to nearly a megawatt circulating in the arms. Each arm contains a Fabry-Perot cavity formed by mirrors at the input and end of the arm. The laser light bounces back and forth between these mirrors about 280 times before leaving the cavity. This effectively increases the arm length from 4 kilometers to over 1,000 kilometers, amplifying the effect of passing gravitational waves. The mirrors must be positioned to a fraction of a wavelength for the cavity to resonate properly, requiring exquisite control systems. The mirrors themselves are perhaps LIGO's most remarkable components. Each test mass mirror weighs 40 kilograms and is made from ultra-pure fused silica. The mirror surfaces are polished to atomic smoothness, with imperfections smaller than a nanometer. The mirrors are coated with alternating layers of silica and tantalum, creating a surface that reflects more than 99.999% of the incident light. These mirrors are suspended by a complex system designed to isolate them from all external vibrations. Each mirror hangs from a quadruple pendulum system, 4 masses connected by thin fibers. This system acts as a mechanical filter, attenuating vibrations more and more at each stage. By the time vibrations reach the bottom mass, the mirror itself, they've been reduced by factors of billions. The suspension fibers are themselves remarkable. Made from fused silica, the same material as the mirrors, they're pulled from larger pieces while heated, creating fibers just 400 micrometers thick, but strong enough to support the 40-kilogram mirrors. Silica fibers were chosen because they have extremely low mechanical loss, meaning vibrations in the fibers die out quickly rather than persisting as noise. The entire suspension system sits on an active seismic isolation platform. This platform uses sensors to detect ground motion and actuators to cancel it out, similar to noise-cancelling headphones but for seismic waves. The system can reduce ground motion by factors of millions at the frequencies where LIGO is most sensitive. Even with this isolation, LIGO must still contend with seismic noise from earthquakes around the world, and even from ocean waves crashing on distant shores. The vacuum system is another engineering marvel. The beam tubes contain about 10,000 cubic meters of vacuum, evacuated to a pressure of about 1/trillionth of an atmosphere. At this pressure, a molecule of gas travels an average of about 40 million kilometers before hitting another molecule, far longer than the path of the laser light through the interferometer. Creating and maintaining this vacuum required years of pumping and careful preparation of all internal surfaces. Temperature control is critical throughout LIGO. Temperature changes cause materials to expand and contract, creating noise that could swamp gravitational wave signals. The mirror surfaces are maintained at a constant temperature to within microkelvins. The entire detector is housed in buildings with sophisticated climate control systems. Even the heat from the laser itself must be carefully managed to prevent thermal distortions in the mirrors. LIGO operates at the quantum limit of measurement precision. The Heisenberg uncertainty principle creates unavoidable noise in the measurement. This quantum noise manifests in 2 ways. At high frequencies, shot noise dominates, caused by the random arrival times of photons at the photodetector. At low frequencies, radiation pressure noise dominates, caused by the random momentum kicks as photons bounce off the mirrors. To reduce quantum noise, LIGO uses a technique called squeezed light. By manipulating the quantum state of the laser light, scientists can reduce noise in one quantity, say position, at the expense of increased noise in another quantity, momentum. Since LIGO only needs to measure position precisely, this trade-off improves sensitivity. The squeezed light system involves nonlinear crystals and additional optical cavities, adding another layer of complexity to an already complex system. The control systems that keep LIGO operational are extraordinarily sophisticated. Hundreds of feedback loops monitor and adjust every aspect of the detector. The arm lengths must be controlled to keep the cavities resonating. The mirror angles must be adjusted to keep the beam centered. The laser frequency must be locked to the arm cavities. All these systems must work together seamlessly, responding to disturbances in microseconds while remaining stable over hours of operation. Data from LIGO streams out at an enormous rate. The main gravitational wave channel is sampled 16,000 times per second, but there are also thousands of auxiliary channels monitoring everything from seismic motion to laser power to mirror positions. This data helps identify noise sources and verify that the detector is operating properly. When a potential gravitational wave signal is detected, these auxiliary channels help confirm that it's not an instrumental artifact. The sensitivity of LIGO is almost beyond comprehension. It can detect changes in the 4-kilometer arm length of less than 10 to the negative 19 meters, smaller than 1/10,000th the width of a proton. This is equivalent to measuring the distance to the nearest star, Proxima Centauri, to within the width of a human hair. It's like detecting the expansion of Earth's orbit due to someone jumping on the sun. This extraordinary sensitivity comes at a price. LIGO is sensitive to everything, not just gravitational waves. Planes flying overhead, trains passing kilometers away, even storms in the Atlantic Ocean create noise in the detector. Scientists have had to develop sophisticated techniques to identify and remove these noise sources. Some noise can be predicted and subtracted. Other noise must be identified and the affected data discarded. The commissioning of LIGO, bringing it from construction to full sensitivity, took years of painstaking work. Every subsystem had to be tested and optimized. Noise sources had to be tracked down and eliminated. The detector's response had to be calibrated precisely. This process required the combined efforts of hundreds of scientists and engineers, each contributing expertise in optics, mechanics, electronics, vacuum systems, or data analysis. LIGO represents a triumph of big science, large-scale collaborative research requiring resources beyond what any single institution could provide. The National Science Foundation has invested over $1 billion in LIGO over several decades. Thousands of scientists from around the world contribute to its operation and data analysis. It's a testament to what humanity can achieve when we work together toward a common goal. But LIGO is more than just a technological marvel. It's a new sense organ for humanity, allowing us to perceive the universe in a fundamentally new way. Just as the invention of the telescope revealed a cosmos far larger and more complex than anyone had imagined, LIGO has opened a new window on the universe, one that shows us the dark side of the cosmos, the violent events that emit no light but shake the very fabric of space and time. The success of LIGO has inspired plans for even more sensitive detectors. Future upgrades will push LIGO to even greater sensitivity. New detectors are being built in Japan and India. Plans are underway for third-generation detectors that will be 10 times more sensitive than current instruments. These future detectors will turn gravitational wave detection from rare events to routine observations, opening up gravitational wave astronomy as a new field of science. The date was September 14th, 2015. It was a Monday morning, and advanced LIGO had been operating in observation mode for just 2 days. The decades of preparation, the years of construction and commissioning, the centuries of human curiosity about the nature of gravity, all converged on this moment. At 9:50 and 45 seconds Universal Time, a gravitational wave that had been traveling through space for over 1 billion years finally reached Earth. The wave hit the Livingston detector first, stretching and squeezing the 4-kilometer arms by a distance smaller than the nucleus of an atom. 7 milliseconds later, the same wave passed through the Hanford detector, 3,000 kilometers away. In that brief moment, lasting just 0.2 of a second, humanity crossed a threshold. We had directly detected gravitational waves for the first time, confirming Einstein's century-old prediction and opening an entirely new way of observing the universe. The signal appeared in the data as a characteristic chirp, a rapid increase in both frequency and amplitude that lasted about 0.2 of a second in LIGO's sensitive band. It started at 35 Hz, too low for human ears to hear, and swept up to over 250 Hz before disappearing. If you could have heard it, it would have sounded like a brief upward sweep, a cosmic whoop that announced the collision of two black holes. Marco Drago, a postdoctoral researcher in Hanover, Germany, was the first person to see the signal. He was monitoring LIGO data remotely when the detection pipeline flagged an event. At first, he thought it must be a test, what the collaboration calls a blind injection, a fake signal added to the data to test the detection and analysis procedures. But this was no test. The signal was real, stronger and cleaner than anyone had expected for a first detection. The automatic detection systems had triggered within 3 minutes of the signal's arrival, sending alerts to team members around the world. But because LIGO was still in engineering mode, not yet officially taking science data, many people initially assumed it was a hardware injection or some kind of test. It took several hours of checking and double-checking before the team began to realize they might have something extraordinary. The signal was remarkably clear, so clear that you could see it by eye in the data without sophisticated processing. In presentations, scientists would later show the raw data, and there it was, the chirp pattern standing out clearly against the background noise. This clarity was both exciting and concerning. Could something so perfect be real, or was it too good to be true? The LIGO team immediately began an intensive process of verification. They checked all the auxiliary channels, the thousands of sensors monitoring every aspect of the detector. Was there any sign of instrumental problems? Had anything unusual happened at either site? They examined data from seismometers, magnetometers, microphones, and dozens of other environmental monitors. Everything appeared normal. Both detectors had been operating smoothly, with no signs of the glitches or disturbances that could mimic a gravitational wave signal. The coincidence between the two detectors was crucial. The signal appeared in both detectors with exactly the time delay expected for a gravitational wave traveling at the speed of light between Louisiana and Washington. The waveforms matched almost perfectly when accounting for the different orientations of the detectors and the expected differences in their responses. This agreement was far too precise to be coincidence or terrestrial interference. Over the following days and weeks, the collaboration performed increasingly sophisticated analyses. They compared the detected signal to hundreds of thousands of theoretical templates, waveforms calculated from Einstein's equations for different combinations of masses and spins. The best match was stunning in its precision. Two black holes, one about 36 times the mass of our Sun, the other about 29 solar masses, spiraling together and merging to form a single black hole of about 62 solar masses. The missing 3 solar masses, the difference between the initial and final black hole masses, had been converted entirely into gravitational wave energy, according to Einstein's E equals mc squared. In the final fraction of a second, this merger released more power in gravitational waves than all the stars in the observable universe combined emit in light. It was the most powerful event humans had ever detected. Yet it happened over 1 billion light-years away and moved our detectors by less than the width of an atomic nucleus. The collaboration maintained strict secrecy while they verified the detection. They knew the stakes were enormous. A false claim of detection would be devastating for the field. But as check after check confirmed the signal's authenticity, excitement built within the collaboration. They had done it. After decades of work, after all the doubts and setbacks, they had detected gravitational waves. The signal was given the designation GWFUM Zone 914 for Gravitational Wave 2015 September 14th. As the team studied it more carefully, they extracted increasingly detailed information about the source. The black holes had been spinning, though not at their maximum possible rates. The final black hole was spinning at about 67% of the maximum allowed by general relativity. The merger had occurred about 1.3 billion light-years away, in the general direction of the southern constellation Volans, though the poor sky localization with just 2 detectors meant the source could have been anywhere in a large region of the southern sky. The waveform matched the predictions of general relativity with extraordinary precision. The signal showed the 3 distinct phases expected for a binary black hole merger: the inspiral, where the 2 black holes orbit each other with increasing frequency; the merger, where the event horizons touch and combine; and the ring down, where the distorted final black hole settles into a stable state. Each phase appeared exactly as Einstein's equations predicted, providing the strongest test yet of general relativity in the strong field regime. What made this detection particularly remarkable was that it came from a type of system many astronomers didn't expect to see. Before LIGO, there was considerable debate about whether binary black holes existed at all, and if they did, whether they would merge within the age of the universe. The detected black holes were also more massive than most astronomers expected for stellar mass black holes. The discovery immediately told us something new about the population of black holes in the universe. The statistical significance of the detection was overwhelming. The probability that random noise could have produced such a signal by chance was less than 1 in 3.5 million. When the collaboration announced the discovery 5 months later, on February 11, 2016, they could state with confidence that gravitational waves had been directly detected for the first time in history. The announcement sent ripples through the scientific community and beyond. It made front-page news around the world. Einstein was right, the headlines proclaimed, though Einstein himself had doubted whether gravitational waves would ever be detected. The discovery was immediately recognized as one of the most important scientific achievements of the century, confirming a fundamental prediction of general relativity and opening an entirely new field of astronomy. For the scientists who had worked on LIGO, many for their entire careers, it was a moment of triumph and vindication. Rainer Weiss, Kip Thorne, and Ronald Drever, the founders of LIGO, had pursued this dream for 40 years. Thousands of other scientists and engineers had contributed to making it reality. Some had passed away before seeing their life's work succeed. Others, particularly young scientists who had joined the project despite warnings that it might never detect anything during their careers, suddenly found themselves at the forefront of a new field. The detection also validated the approach of big science. LIGO had cost over $1 billion and taken decades to build. Many had questioned whether such resources should be devoted to detecting something that might not exist or might be too weak to ever observe. But the investment had paid off spectacularly, not just in the detection itself, but in the technologies developed along the way, and the international collaboration it had fostered. GW 914 was just the beginning. During advanced LIGO's first observing run, from September 2015 to January 2016, 2 more gravitational wave signals were detected. The second, GW 151226, came from lighter black holes, about 14 1/8 solar masses, and was visible in LIGO's band for about a full second. The third was a marginal detection, not quite significant enough to claim definitively, but consistent with another binary black hole merger. These early detections revealed a population of binary black holes that astronomers hadn't known existed. The black holes were more massive than expected from stellar evolution models. They were merging frequently enough that LIGO could detect several in just a few months of operation. Each detection added to our understanding of black holes, testing general relativity in new ways and revealing the dark side of the universe that electromagnetic observations couldn't see. The technical achievement of detecting JW 150914 cannot be overstated. The signal stretched and compressed the 4-kilometer arms of LIGO by about 4 times 10 to the negative 18 meters. To put this in perspective, if LIGO's arms were scaled up to span the entire Milky Way galaxy, 100,000 light-years across, the gravitational wave would have changed this distance by about the width of a human hair. The fact that we can measure such impossibly small effects is a testament to human ingenuity and persistence. The detection technique itself was a masterpiece of data analysis. The signal was extracted using matched filtering, comparing the data to hundreds of thousands of theoretical templates. This technique, developed over decades, allowed LIGO to pull signals out of noise even when the signal was weaker than the noise itself. It's like hearing a conversation across a noisy room by knowing in advance what might be said. The implications of the detection rippled outward through physics and astronomy. It confirmed that black holes exist and can form binary systems. It showed that these binaries merge within the age of the universe. It demonstrated that gravitational waves travel at the speed of light and behave exactly as general relativity predicts. It even provided a new test of the equivalence principle, one of the foundations of general relativity. For cosmology, the detection offered a new way to measure distances in the universe. Gravitational waves are standard sirens, sources whose intrinsic brightness is determined by their dynamics. By measuring the amplitude of the waves, astronomers can determine the distance to the source. This provides a completely independent way to measure cosmic distances, potentially helping resolve tensions in our understanding of cosmic expansion. The detection also had profound philosophical implications. It showed that spacetime itself is a dynamic physical entity that can ripple and carry energy. It connected human technology to some of the most extreme events in the universe, black holes colliding billions of light years away. It demonstrated that with sufficient cleverness and persistence, humans can detect phenomena that seem impossibly beyond our reach. The discovery of gravitational waves from merging black holes revealed a hidden universe of dark objects engaged in violent dances. Each detection tells a story written in the language of rippling spacetime, stories of black holes that lived and died in distant galaxies, leaving only their gravitational echoes to mark their passing. These cosmic songs, brief chirps lasting fractions of a second, carry information about some of the most extreme objects and events in the universe. Black holes, by their very nature, are invisible to traditional astronomy. They emit no light, reflect no radiation, and can only be detected through their gravitational influence on nearby matter, or, now, through the gravitational waves they produce when they collide. Before LIGO, astronomers knew of only a handful of stellar mass black holes, all detected because they were pulling matter from companion stars. The population of isolated black holes or black hole binaries remained completely hidden. The gravitational wave signals from black hole mergers are remarkably information-rich. The frequency and amplitude of the waves depend on the masses of the black holes. The rate at which the frequency changes tells us how quickly they're spiraling together. The detailed shape of the waveform reveals the black hole's spins, how fast they're rotating, and in what direction relative to their orbit. Even the final ring down, lasting just milliseconds, carries information about the mass and spin of the merged black hole. Each black hole merger LIGO and Virgo have detected has revealed something new about these dark objects. The first detection, GW50914, surprised astronomers with its heavy black holes around 30 solar masses each. Before this, most astronomers expected stellar mass black holes to top out around 15 or 20 solar masses. The existence of heavier black holes suggested either that our understanding of stellar evolution was incomplete, or that these black holes had grown through previous mergers. The range of black hole masses detected has been remarkable. LIGO and Virgo have seen black holes from about 5 solar masses, close to the minimum mass for black hole formation, up to nearly 100 solar masses, pushing against theoretical limits for black holes formed from stars. This diversity tells us about the variety of stellar deaths and the different environments where black holes form and evolve. The spins of merging black holes carry their own stories. A black hole's spin is a fossil record of its formation and growth. Black holes formed from the collapse of rotating stars should be spinning rapidly. Black holes that grew by swallowing matter from a disk should also spin quickly, as the infalling matter carries angular momentum. But black holes that grew through mergers with randomly oriented spins might rotate slowly. The distribution of spins LIGO and Virgo observe helps distinguish between different formation scenarios. Some detected mergers have shown clear signs that at least one black hole was spinning rapidly, with the spin axis tilted relative to the orbital plane. This precession causes the orbital plane to wobble, creating a characteristic modulation in the gravitational wave signal. These precessing systems are particularly valuable because they allow more precise measurements of the black hole properties and provide additional tests of general relativity. The rate at which black holes merge throughout the universe was another surprise. Before LIGO's detections, estimates range from pessimistic predictions of less than one merger per year in the observable universe to optimistic predictions of hundreds per year. The actual rate fell somewhere in between, but toward the optimistic end, with LIGO and Virgo detecting dozens of mergers per year when operating at design sensitivity. This merger rate has profound implications for our understanding of stellar evolution and black hole formation. It suggests that massive stars in binary systems can survive the violent deaths of both stars, leaving behind a black hole binary. Alternatively, black holes might find each other in dense stellar environments like globular clusters, forming binaries through gravitational interactions. The observed population likely includes black holes from both formation channels. The distribution of black hole masses provides clues about the lives and deaths of massive stars. There appears to be a relative lack of black holes between about 50 and 120 solar masses, possibly indicating a pair instability supernova gap. In this mass range, dying stars might be completely disrupted rather than collapsing to black holes. The existence and location of this gap teaches us about nuclear physics in stellar cores and the final stages of massive star evolution. Some mergers have been particularly intriguing. GW1904-2 was the first clear detection of black holes with significantly unequal masses, about 30 and 8 solar masses. The mass symmetry allowed for additional tests of general relativity and revealed higher harmonic modes in the gravitational waves, like overtones in a musical instrument. GW1908 Thor involved a 23 solar mass black hole merging with a mystery object of 2.6 solar masses, either the lightest black hole or the heaviest neutron star ever discovered. The most massive system detected so far, GW1905-21, involved black holes of about 85 and 66 solar masses, merging to form a black hole of about 142 solar masses. This was particularly exciting because the heavier black hole fell squarely in the predicted pair instability gap, suggesting it might itself be the product of a previous merger. The final black hole was the first clear detection of an intermediate mass black hole, bridging the gap between stellar mass and supermassive black holes. These observations are teaching us about black hole genealogy. If black holes can merge, and the products of those mergers can merge again, then some of the black holes we detect might be second or even third generation, carrying the combined mass of multiple stellar ancestors. This hierarchical merging might explain some of the surprisingly massive black holes LIGO and Virgo have detected. The gravitational waves from black hole mergers also serve as laboratories for testing general relativity under the most extreme conditions. Near merging black holes, space-time curvature is enormous. Velocities approach the speed of light, and nonlinear effects become important. Every aspect of the detected waveforms has matched general relativity's predictions perfectly. No deviations have been found, despite physicists' best efforts to find them. These tests of general relativity are remarkably stringent. The theory must correctly predict the spiral driven by gravitational wave emission. It must describe the violent merger, where space-time curvature is extreme and nonlinear effects dominate. And it must predict the ring-down, where the merged black hole vibrates in specific patterns determined by its mass and spin. The agreement between observation and theory across all these regimes is a triumph for Einstein's century-old theory. The ring-down phase is particularly interesting because it allows tests of the black hole no-hair theorem. This theorem states that black holes are completely characterized by just three properties: mass, spin, and electric charge. Since astrophysical black holes are expected to be electrically neutral, only mass and spin matter. The ring-down frequencies and damping times depend only on these two parameters. By measuring multiple ring-down modes, physicists can test whether the merged object really is a black hole as described by general relativity. Beyond testing general relativity, black hole mergers are revealing the environments where these events occur. The lack of electromagnetic counterparts to most black hole mergers suggests they occur in relatively empty regions of space, consistent with old binary systems that have had billions of years to spiral together. But some mergers might occur in denser environments, possibly in the accretion disks around supermassive black holes or in stellar clusters. The black holes detected by LIGO and Virgo are also contributing to our understanding of cosmic history. The mergers we detect today involve black holes that formed from stars that died millions or billions of years ago. By studying the population of merging black holes at different distances, corresponding to different times in cosmic history, we can learn about star formation and stellar evolution across cosmic time. These observations have implications for the growth of supermassive black holes in galaxy centers. While stellar mass black holes can't grow directly into million or billion solar mass monsters, intermediate mass black holes formed through hierarchical mergers might serve as seeds. If such seeds formed early in cosmic history, they could have grown through accretion and additional mergers into the supermassive black holes we see today. The songs of merging black holes have also revealed the existence of black hole deserts and oases in the universe. Some regions of parameter space, certain combinations of masses and spins, seem populated with merging black holes. Others appear empty. These patterns tell us about the astrophysical processes that create and bring together binary black holes. Each new detection adds another verse to the cosmic symphony we're learning to hear. Some mergers chirp quickly, lightweight black holes spiraling together in a rapid crescendo. Others rumble slowly, massive black holes taking their time before the final plunge. Some sing purely, equal mass systems producing clear, strong signals. Others warble with complexity, unequal masses and tilted spins creating rich harmonics. On August 17, 2017, gravitational wave astronomy entered a new era. For the first time, astronomers detected both gravitational waves and light from the same cosmic event, the merger of two neutron stars in a galaxy 130 million light-years away. This detection, designated JU 70817, marked the birth of multi-messenger astronomy with gravitational waves and revealed that colliding neutron stars are cosmic alchemists, forging heavy elements like gold and platinum in their violent death throes. The gravitational wave signal from JU 70817 was different from the black hole mergers LIGO and Virgo had been detecting. It lasted much longer, about 100 seconds in LIGO's sensitive band, compared to fractions of a second for most black hole mergers. The signal started at a lower frequency and swept upward more gradually, reflecting the smaller masses of neutron stars compared to the black holes previously detected. Each neutron star was between about 1.1 and 1.6 solar masses, typical for these ultra-dense objects. Just 1.7 seconds after the gravitational waves passed Earth, NASA's Fermi satellite detected a short gamma-ray burst, a brief flash of the most energetic form of light. This near-simultaneous arrival, after the signals had travelled for 130 million years, confirmed that gravitational waves travel at the speed of light to extraordinary precision. It also immediately told astronomers that this was something special. Black hole mergers don't produce light, but neutron star mergers do. The coincident detection triggered one of the most intensive astronomical observation campaigns in history. Within hours, telescopes around the world and in space were searching for the source. The gravitational wave signal from 3 detectors, the 2 LIGO instruments and Virgo in Italy, had localized the source to a region of about 30 square degrees in the southern sky. The gamma-ray detection helped refine this position. Less than 11 hours after the merger, astronomers at the SWOPE telescope in Chile found it, a new point of light in the galaxy NGC 4993, a galaxy that hadn't shown any such source in previous observations. The discovery triggered a frenzy of follow-up observations. Within days, over 70 telescopes had observed the event across the entire electromagnetic spectrum, from radio waves to gamma rays. Never before had a single astronomical event been studied in such detail. What astronomers saw was remarkable. The optical light from the merger was unlike any supernova or other known transient. It started blue and bright, then faded and reddened over the following days. This behavior matched theoretical predictions for a kilonova, an event powered by the radioactive decay of heavy elements created in the merger. The light curves and spectra provided the first direct evidence that neutron star mergers create heavy elements through rapid neutron capture, the R process. The R process is one of nature's most extreme nuclear physics experiments. In the incredibly neutron-rich environment created when neutron stars collide, atomic nuclei capture neutrons faster than they can radioactively decay. This builds up highly unstable, neutron-rich isotopes that then decay back towards stability, creating heavy elements along the way. The process happens in seconds but creates elements that take billions of years to form in other environments. The spectra of G17081's kilonova showed clear signatures of heavy elements that had just been synthesized. Astronomers identified features from strontium, a relatively light R process element, and evidence for lanthanides, heavy rare earth elements. The total mass of R process elements produced was estimated at about 10,000 Earth masses, including several Earth masses of gold and platinum. This single event created more gold than exists in all of Earth's crust. This discovery solved a long-standing mystery in astronomy. Where do heavy elements come from? While elements up to iron can be created in stellar cores through fusion, heavier elements require different processes. For decades, astronomers debated whether heavy elements were primarily created in supernovae or in neutron star mergers. G17081 showed that neutron star mergers are prolific producers of heavy elements, possibly the dominant source in the universe. The implications extend to our own existence. The gold in jewelry, the platinum in catalytic converters, the uranium in nuclear reactors, all were likely created in neutron star mergers billions of years ago. These elements were dispersed into space, enriching the gas clouds from which new stars and planets formed. The Earth and everything on it contains atoms forged in these cosmic collisions. The gravitational wave signal itself revealed remarkable physics. Unlike black holes, neutron stars are made of matter, not just curved spacetime. As the neutron stars spiraled closer together, tidal forces began to deform them. This deformation left subtle imprints on the gravitational waves, allowing scientists to measure the squishiness of neutron star matter. These measurements constrain the equation of state of matter at nuclear densities, conditions impossible to create in Earth laboratories. The final fate of the merged neutron stars remained somewhat uncertain. The total mass was close to the maximum mass a neutron star can support. The merger might have immediately formed a black hole, or it might have created a hypermassive neutron star, temporarily supported by rapid rotation, that collapsed to a black hole milliseconds or seconds later. The gravitational wave signal cut off as the neutron stars merged, just as they entered LIGO's most sensitive frequency range, leaving the final outcome ambiguous. The gamma-ray burst associated with G708 was peculiar. It was much fainter than typical short gamma-ray bursts, suggesting we were viewing it from an angle rather than head-on. This confirmed theoretical predictions that gamma-ray bursts are beamed, concentrated in jets rather than emitted equally in all directions. The fact that we saw it at all, despite the unfavorable viewing angle, suggests that neutron star mergers might be the source of all short gamma-ray bursts, mysterious flashes that astronomers had been detecting for decades. Radio and X-ray observations continued for months after the merger, tracking the afterglow as the ejected material ploughed into the surrounding interstellar medium. These observations revealed the emergence of a relativistic jet, a beam of material moving at close to the speed of light. The jet took weeks to break through the cloud of ejected material, explaining the delayed brightening in X-rays and radio waves. The multi-wavelength observations painted a complete picture of the merger and its aftermath. The gravitational waves revealed the spiraling dance of the neutron stars. Gamma rays marked the moment of merger. Optical and infrared light showed heavy element synthesis. X-rays and radio waves trace the expanding blast wave. Each messenger told part of the story, and together they provided an unprecedented view of one of the universe's most extreme events. Q708b107 also demonstrated the power of coordinated astronomical observations, the rapid communication between gravitational wave observatories and electromagnetic telescopes, the swift response of observers worldwide, and the open sharing of data enabled discoveries that no single team could have made alone. It was a triumph of international scientific collaboration. The event rate for neutron star mergers detectable by current gravitational wave observatories is lower than for black hole mergers, perhaps a few to tens per year. This relative rarity makes each detection precious. But future detectors will be sensitive enough to detect neutron star mergers from much greater distances, potentially finding hundreds per year. Each will offer new insights into nuclear physics, heavy element creation, and the deaths of massive stars. The discovery has also opened new possibilities for cosmology. Gravitational waves from neutron star mergers serve as standard sirens, sources whose intrinsic brightness is known from the gravitational wave signal. When combined with electromagnetic observations that reveal the host galaxy's redshift, these events can measure the expansion rate of the universe. GW10817 provided the first such measurement, though with large uncertainties. Future detections will refine these measurements, potentially resolving current tensions in cosmology. Neutron star mergers might also create other exotic phenomena. Some models suggest they could produce strangelets, hypothetical particles made of strange quark matter. They might create cosmic rays, high-energy particles that bombard Earth from space. They could even produce detectable neutrino signals, adding another messenger to study these events. The detection of G+10817 fulfilled the promise of multi-messenger astronomy that had motivated gravitational wave detection for decades. It showed that gravitational waves aren't just an alternative to electromagnetic observations, but a complement to them. Together, gravitational waves and electromagnetic signals provide a more complete understanding than either could offer alone. The universe is filled with gravitational waves at every frequency, from the rapid vibrations of colliding stellar mass black holes to the slow undulations from orbiting supermassive black holes that take years to complete a single cycle. This cosmic symphony spans more than 20 orders of magnitude in frequency, each band carrying information about different sources and different eras in cosmic history. Learning to hear this full spectrum is one of the great challenges and opportunities in modern astronomy. Current ground-based detectors like LIGO and Virgo are sensitive to gravitational waves with frequencies between about 10 and several thousand hertz. This range is well matched to the final moments of stellar mass compact object mergers. But this is just one octave in the gravitational wave spectrum. Other frequencies require different detection strategies, from space-based interferometers to pulsar timing arrays to cosmological observations. At the lowest frequencies, below about 1 nanohertz, gravitational waves have wavelengths comparable to the observable universe. These primordial gravitational waves, if they exist, would have been created in the first fraction of a second after the Big Bang. They would carry information about the universe's birth, potentially including signatures of cosmic inflation, the hypothesized period of exponential expansion that set the stage for the Big Bang. Detecting primordial gravitational waves is extraordinarily challenging. These waves would be incredibly weak, and they would appear not as passing waves but as a pattern of polarization in the cosmic microwave background, the afterglow of the Big Bang. Several experiments have searched for this B-mode polarization, and while some have detected B-modes from gravitational lensing, the primordial signal remains elusive. Moving up in frequency, between about 1 nanohertz and 1 microhertz, we enter the realm of pulsar timing arrays. These use millisecond pulsars, rapidly spinning neutron stars that emit radio pulses with extraordinary regularity as cosmic clocks. Gravitational waves passing between Earth and a pulsar change the arrival times of the pulses. By monitoring many pulsars for years or decades, astronomers can search for the correlated timing changes that would indicate gravitational waves. The primary sources in this frequency band are supermassive black hole binaries, pairs of million or billion solar mass black holes orbiting each other in the centers of merging galaxies. These systems take years to complete an orbit, producing gravitational waves at nanohertz frequencies. The combined signal from many such binaries throughout the universe should create a gravitational wave background, a random superposition of waves from different directions. In 2023, pulsar timing arrays announced strong evidence for this gravitational wave background. The NanoGrav collaboration in North America, the European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and the Indian Pulsar Timing Array all reported consistent signals. While not yet a definitive detection, this evidence suggests we're beginning to hear the bass notes of the cosmic gravitational wave symphony. Between about 1 microhertz and 1 hertz lies a gap in our current gravitational wave sensitivity, sometimes called the gravitational wave desert. Ground-based detectors can't operate at these low frequencies because of seismic noise, while pulsar timing arrays lose sensitivity at higher frequencies. But this desert is expected to be populated with interesting sources, including intermediate mass black hole mergers and the early spiral of stellar mass binaries. The Laser Interferometer Space Antenna, or LISA, will explore this frequency range. Scheduled for launch in the 2037, LISA will consist of 3 spacecraft separated by 2.5 million kilometers, forming a giant triangular interferometer in space. Free from seismic noise and with much longer arms than ground-based detectors, LISA will detect gravitational waves from about 10 microhertz to 1 hertz. LISA's sources will be diverse and numerous. It will detect merging supermassive black holes out to enormous distances, potentially seeing every major galaxy merger in the observable universe. It will observe extreme mass ratio in spirals, where stellar mass compact objects spiral into supermassive black holes. These signals can last for years, allowing precise mapping of spacetime near the supermassive black hole. Perhaps most remarkably, LISA will detect tens of thousands of binary white dwarfs in our own galaxy. These systems, pairs of Earth-sized stellar remnants orbiting each other, are so numerous that at low frequencies their signals will blur together into a confusion foreground. At higher frequencies, individual systems will stand out, providing a census of compact binaries in the Milky Way. Some of these white dwarf binaries will be verification binaries, systems already known from electromagnetic observations. These will serve as calibration sources for LISA, allowing scientists to verify the detector's performance. A few systems, like HM Cancri with an orbital period of just 5.4 minutes, are such strong gravitational wave sources that LISA should detect them within weeks of beginning observations. LISA will also search for exotic sources like cosmic strings, hypothetical one-dimensional defects in spacetime that might have formed in the early universe. If they exist, cosmic strings could produce distinctive gravitational wave signatures as they oscillate and occasionally intersect. While speculative, the detection of cosmic strings would revolutionize our understanding of fundamental physics. Looking to the future, third-generation ground-based detectors will dramatically expand our reach. The Einstein telescope in Europe and Cosmic Explorer in the United States will have arms 10 to 40 kilometers long and sensitivity 10 times better than current detectors. They will detect black hole mergers throughout the observable universe and neutron star mergers from billions of light-years away. These future detectors will do more than just detect more events. They will measure source properties with extraordinary precision, determining masses to better than 1% and spins to a few percent. They will enable precision tests of general relativity, potentially revealing deviations that could point to new physics. They will detect gravitational waves from core collapse supernovae in our galaxy, revealing the dynamics of stellar death. The improved sensitivity will also enable new types of observations. Third-generation detectors might detect continuous gravitational waves from spinning neutron stars with smaller symmetries. They could observe the gravitational wave memory effect, a permanent displacement caused by the passage of gravitational waves. They might even detect the stochastic background from all the unresolved sources throughout the universe. Space-based detectors beyond LISA are also being considered. DeSigo, a proposed Japanese mission, would fill the gap between LISA and ground-based detectors. The Big Bang Observer, a more distant prospect, would search for primordial gravitational waves from inflation. Tianqin, a Chinese mission, would observe gravitational waves using a geocentric orbit. Each frequency band offers unique science opportunities. Low-frequency observations with pulsar timing arrays probe the most massive black holes in the larger scales. Mid-frequency observations with LISA study galactic binaries and intermediate mass systems. High-frequency observations with ground-based detectors catch the final moments of stellar mass mergers. Together, they provide a complete view of the gravitational wave universe. The technology for detecting gravitational waves continues to advance. Quantum squeezing is reducing quantum noise in current detectors. Cryogenic mirrors might reduce thermal noise in future detectors. Novel interferometer configurations could improve sensitivity at specific frequencies. Machine learning algorithms are getting better at identifying signals and removing noise. Alternative detection methods are also being explored. Atom interferometry could provide complementary sensitivity to laser interferometry. Resonant bar detectors, descendants of Weber's original design but vastly more sensitive, might detect very high-frequency gravitational waves. Even the Earth and Moon could serve as gravitational wave detectors, with seismometers searching for the normal modes excited by passing waves. The gravitational wave spectrum might also contain surprises. Phase transitions in the early universe could have produced gravitational waves with unique signatures. Dark matter, if it consists of primordial black holes or other massive compact objects, would create a gravitational wave background. Exotic objects like boson stars or Griver stars, if they exist, would produce distinctive gravitational wave signals. As we open new frequency bands and improve sensitivity, we're certain to discover unexpected sources. The history of astronomy shows that every new window on the universe reveals surprises. Radio astronomy discovered pulsars and quasars. X-ray astronomy revealed black holes and neutron stars. Gravitational wave astronomy has already surprised us with heavy stellar mass black holes and prolific R-process element production. Future surprises await. The full gravitational wave spectrum will tell the complete story of structure formation in the universe. From quantum fluctuations in the infant universe that seeded all structure, to the formation and growth of black holes, to the mergers that punctuate galactic evolution, gravitational waves carry information about every epoch. As we learn to hear more of this cosmic symphony, we're piecing together the biography of the universe itself. As we stand at the dawn of gravitational wave astronomy, we can only imagine what discoveries lie ahead. The successful detection of gravitational waves has opened a new sense for humanity, allowing us to feel the universe in a way that was impossible just a decade ago. The future promises not just more detections, but qualitatively new insights into the cosmos, from the nature of gravity itself to the origins of the universe, and the fate of matter under extreme conditions. The immediate future is bright with planned improvements to existing detectors. LIGO and Virgo are undergoing upgrades that will double their sensitivity by the late 2020s. The Kagura detector in Japan, built underground to reduce seismic noise, is coming online. LIGO India, a third LIGO detector being built in India, will dramatically improve sky localization when it begins operations. With 5 detectors operating in a global network, we'll be able to pinpoint sources to within a few square degrees, enabling rapid electromagnetic follow-up. These improvements aren't just about detecting more events, though the detection rate will increase dramatically. With better sensitivity comes better precision in measuring source properties. We'll determine masses, spins, and distances more accurately. We'll detect weaker features in the waveforms that reveal subtle effects like orbital precession and higher-order modes. Each improvement in precision is an opportunity to test general relativity more stringently and search for new physics. The population of detected sources will grow from dozens to thousands. This statistical sample will reveal patterns invisible in individual detections. We'll map how black hole masses and spins vary with cosmic time, tracing the evolution of stellar populations across the universe. We'll determine whether black holes have preferred masses, gaps in their mass distribution, or correlations between mass and spin that reveal their formation mechanisms. Neutron star observations will unlock the mysteries of matter at nuclear densities. Each neutron star merger provides constraints on the equation of state, the relationship between pressure and density in neutron star cores. With enough observations, we'll determine whether neutron star cores contain exotic matter like hyperons or quark matter. We'll measure the maximum mass a neutron star can have before collapsing to a black hole, a fundamental limit set by nuclear physics. The combination of gravitational wave and electromagnetic observations will become routine. Networks of robotic telescopes stand ready to respond to gravitational wave alerts within seconds. Future detections like GBUS 717 will be observed from the first moments, capturing physics invisible in delayed observations. We'll see the shock breakout as jets punch through merger ejecta, the earliest kilonova emission, and perhaps even prompt optical or radio emission from the merger itself. Multi-messenger observations will also reveal the environments where mergers occur. Identifying host galaxies tells us about the stellar populations that produce merging compact objects. Are they found in young star-forming galaxies or old quiescent ones? Do they prefer dense galactic centers or sparse outskirts? These environmental clues help distinguish between different formation scenarios for binary compact objects. The cosmological applications of gravitational waves will mature as we detect more sources. Each neutron star merger with an electromagnetic counterpart provides an independent measurement of cosmic expansion. With hundreds of such measurements, we'll determine the Hubble constant to unprecedented precision, potentially resolving the current tension between measurements from the early and late universe. Gravitational waves might reveal whether dark energy is truly constant or evolves with time. Black hole mergers, while lacking electromagnetic counterparts, will probe cosmology in different ways. Their huge detection volumes mean we can observe them across most of cosmic history. By measuring how the merger rate changes with redshift, we'll trace the history of star formation and black hole growth. Statistical analyses of many events will reveal whether general relativity holds at cosmological scales or whether modifications are needed. The search for continuous gravitational waves will intensify. These steady signals from spinning neutron stars are much weaker than merger signals but last indefinitely, allowing us to integrate data over months or years to build up sensitivity. Detecting continuous waves would reveal neutron stars invisible to electromagnetic observations, perhaps doubling the known population. The strength of these waves depends on neutron star mountains, tiny deviations from perfect sphericity that would tell us about the strength of neutron star crusts. Supernovae in our galaxy will eventually be detected through their gravitational waves. While rare, occurring perhaps a few times per century, a galactic supernova would be a treasure trove of physics. Gravitational waves would reveal the dynamics of core collapse, the bounce when nuclear forces halt the implosion, and the subsequent explosion. Combined with neutrino and electromagnetic observations, we'd have a complete picture of stellar death. The most exotic sources remain to be discovered. Cosmic strings, if they exist, would produce unique gravitational wave signatures as they oscillate and reconnect. Phase transitions in the early universe might have created a background of gravitational waves with a characteristic spectrum. Dark matter, if it consists of primordial black holes, would create both a confusion background and occasional nearby mergers with distinctive properties. LISA's launch in the 2037 will revolutionize our understanding of supermassive black holes. Every major galaxy merger in the observable universe will be visible to LISA, revealing how galaxies and their central black holes co-evolve. We'll see supermassive black holes with masses from millions to billions of solar masses, spanning the full range that exists in nature. Some mergers might be visible to both LISA and ground-based detectors, as stellar mass black holes merge near supermassive ones. The extreme mass ratio in spirals LISA will detect are natural laboratories for testing general relativity. As a stellar mass object spirals into a supermassive black hole, it samples the space-time geometry over millions of orbits. Any deviation from general relativity's predictions would accumulate over these many orbits, making these systems exquisitely sensitive probes of gravitational theory. We might discover that black holes have hair, properties beyond mass and spin that current theory says they shouldn't have. Third-generation ground-based detectors will push into new territories of physics. The Einstein telescope and cosmic explorer will detect essentially every stellar mass merger in the observable universe, providing a complete census of compact object populations. They'll observe black holes forming in the early universe when the first stars died. They might detect intermediate mass black holes, filling the gap between stellar mass and supermassive black holes. These future detectors will also enable precision tests of fundamental physics. They'll measure the speed of gravity to extraordinary precision, confirming or refuting alternative theories. They'll search for graviton mass. While general relativity says gravitons are massless, a tiny mass would have profound implications. They'll test whether black holes are truly the objects general relativity predicts or something more exotic. The technology developed for gravitational wave detection is already finding applications elsewhere. The exquisite isolation systems help stabilize other precision experiments. The ultra-stable lasers improve atomic clocks and quantum computing. The data analysis techniques apply to any search for weak signals in noise. The international collaboration model shows how global science can tackle grand challenges. Future technologies might enable even more sensitive detectors. Quantum entanglement could reduce noise below classical limits. Atom interferometry might provide an alternative to laser interferometry. Space-based detectors at Earth-Sun Lagrange points could have baselines of millions of kilometers. Networks of small, cheap detectors might provide all-sky, all-time coverage. The philosophical implications of gravitational wave astronomy continue to unfold. We've confirmed that spacetime is a dynamic entity that can ripple and carry energy. We've shown that black holes are real objects that merge and ring. We've connected the atoms in our bodies to neutron star collisions billions of years ago. Each discovery deepens our connection to the cosmos. Educational impacts are already visible. Students who once learned about gravitational waves as abstract theory now see them as observable phenomena. The success of LIGO has inspired a new generation of physicists and engineers. The combination of cutting-edge technology, fundamental physics, and cosmic discovery makes gravitational wave astronomy irresistible to curious minds. International cooperation in gravitational wave astronomy sets an example for global collaboration. Data is shared openly, discoveries are announced jointly, and credit is distributed fairly. This model shows how humanity can work together on challenges that no single nation could tackle alone. As we face global challenges from climate change to pandemics, the gravitational wave community demonstrates the power of cooperation. The economic impacts, while hard to quantify, are real. The technologies developed for gravitational wave detection have commercial applications. The trained scientists and engineers contribute to technological innovation. The inspiration provided by discovery drives interest in science and technology careers. Countries investing in gravitational wave astronomy are investing in their technological future. Looking decades ahead, gravitational wave astronomy will mature from a novel observation method to an essential tool for understanding the universe. Just as electromagnetic astronomy progressed from Galileo's simple telescope to the James Webb Space Telescope, gravitational wave detectors will become increasingly sophisticated. Future astronomers will take gravitational wave observations for granted, unable to imagine astronomy without them. We might discover that the universe is stranger than we imagine. Perhaps black holes connect to other universes through wormholes. Perhaps there are extra dimensions that only gravity can explore. Perhaps the Big Bang was not the beginning, but a transition from an earlier phase. Gravitational waves might reveal any of these possibilities, or surprises we haven't even conceived. The ultimate goal is a complete picture of the universe across all messengers: electromagnetic radiation, gravitational waves, neutrinos, and cosmic rays. Each provides unique information, and together they tell the full story. We're building toward an era of complete astronomical observation, where no cosmic event goes unnoticed, and every phenomenon is understood through multiple channels. As we conclude our journey through the story of gravitational waves, we stand at a remarkable moment in history. we've developed the ability to detect distortions in spacetime smaller than atomic nuclei. We've heard black holes collide from billions of light years away. We've watched neutron stars create gold and platinum before our eyes. And this is just the beginning. The universe is talking to us in a language we've only just learned to understand. Every ripple in spacetime carries information about its source, preserving details of cosmic catastrophes for millions or billions of years until they wash over our detectors. As our ability to read these messages improves, we'll uncover more of the universe's secrets. The detection of gravitational waves represents one of humanity's greatest intellectual achievements. It required a century of theoretical development, decades of technological advancement, and the combined efforts of thousands of scientists and engineers. It pushed the boundaries of human capability and expanded our conception of what's possible. But perhaps most importantly, gravitational wave astronomy reminds us that we're part of something larger. The gold in a wedding ring formed in a neutron star merger. The space-time we inhabit, rippling with waves from distant catastrophes. The black holes scattered throughout the universe, singing their songs in frequencies we've learned to hear. We're connected to the cosmos in ways we're only beginning to understand. As you drift off to sleep tonight, remember that gravitational waves are passing through you right now. Somewhere in the universe, black holes are merging, neutron stars are colliding, and space-time is ringing with their echoes. These waves have traveled for millions or billions of years to reach us, carrying stories of events so powerful they shake the fabric of reality itself. And thanks to human ingenuity and persistence, we can finally hear what the universe has been trying to tell us all along. Sweet dreams! And thank you for joining me on this journey through the remarkable story of gravitational waves. If you enjoyed this cosmic adventure, please consider subscribing to the channel and hitting the notification bell so you won't miss future journeys through the wonders of our universe. Until next time, this is Sleepy Parallax, reminding you that even in the quietest moments, the universe is alive with invisible wonders waiting to be discovered.